I wanted to make specifically kind of coming back to something I mentioned at the beginning of the course. So if you guys remember, in the very first lecture of the course, I talked about this idea of, well, how do we build intelligent machines? And I discussed how, well, it used to be that the way people would think about AI is that they would think, well, okay, intelligence consists of a bunch of different components. There's language, there's speech, there's etc. We build a little module for each of those components. It will solve that little problem, and then we'll wire them all together. And it turns out that that's really hard for two reasons. One is building those modules by hand is next to impossible, and the other one is when you do build them and you wire them together, they don't work together. So I made this argument in the beginning of the course about how perhaps learning might actually be the basis of intelligence, that there's sort of some things that we know how to do well right out of the box, like walking, but there's clearly things that people are really good at doing that can't be sort of built in, like driving a car, because there weren't cars around when humans evolved. So it seems like we can make a compelling argument that learning can serve as one of the bases of intelligence. And if we make that argument, then we might say, well, should we just go back to this little like modular picture and design a separate learning algorithm for each module? Well, maybe not so much, because then we've just sort of taken this problem of designing each of these systems and changed it into a problem of designing each of these learning algorithms. But maybe we don't need a different learning algorithm for each one. So if you remember these pictures from the beginning of the course, that, well, there's sort of a good argument to be made that at least the human brain is kind of homogeneous in the sense that different parts can take on different roles. And if you recall from the beginning of the course, this was a discussion about how, for example, you could train the auditory cortex to do something that looks like vision if you perform a little rewiring experiment. So this maybe leads to the idea that, well, what if there's just sort of one algorithm that's very good at learning all sorts of different things, and if we can just come up with that, then we don't need to have the kind of the modular view of intelligence, and we can just have our really good algorithm that's capable of doing lots of stuff. So then the question that comes up is that, well, what should this algorithm be able to do? And it seems like at the very least it should be able to do two things: deal with high bandwidth sort of complex sensors over here, and then be able to choose complex actions. And that's sort of at a very cartoony level is what tells us that we should perhaps think about deep reinforcement learning, because the deep part is what helps us process complex inputs and also compute really complex functions, and the reinforcement learning part is what helps us take actions. Okay, so to that end, let me just skip through this because I don't have as much time. We learned about a number of different algorithms in the course to help us maybe start thinking about these questions. We learned about the different trade-offs of those algorithms. One question that perhaps is good to ask, and these slides will also be posted on the website, one question that might be good to ask is, after we've learned all these things, well, how do we choose the right algorithm for the job? And they all have so far a number of different trade-offs. So currently sort of the state of this science is that we haven't arrived at here is the thing that everybody should be using, but we have a number of different options with a number of different trade-offs, and also different potential for future development. So you might, for example, think about how general a method is. So model-free algorithms tend to be very general, but perhaps a bit less efficient. Model-based algorithms often introduce some additional assumptions, like, for example, the fact that you can learn a model, which is sometimes easy and sometimes hard. So you have to consider the generality of the method. You have to consider the stability of the method, especially if you're looking at, for example, applying it to complicated real-world systems where you can't necessarily run 1,000 hyperparameter sweeps. You have to consider sample efficiency and walk-log time, which, as we discussed before, are not necessarily the same thing. In fact, sometimes they're actually they run directly counter to one another. So there's a bunch of trade-offs between the methods that we learned. And this is the slide on sample efficiency that you saw before. I'll skip through this. And beyond just the particular methods, there's all this other stuff that surrounds reinforcement learning algorithms. Like, for example, you need some way to specify a reward in order to be able to learn something. And sometimes specifying the reward is very easy, and sometimes it's very hard. So this is from one of the slides that Chelsea covered on inverse reinforcement learning. So beyond just kind of coming up with a good learning algorithm under the standard reinforcement learning assumptions, you need to also make sure that the standard reinforcement learning assumptions actually agree with the problem setting that you're really after. But what about all this stuff? So we covered a lot of interesting models and algorithms, but what about the processing complex senses and taking complex actions and how that relates to intelligence? Well, if we take a step back and think about, what's sort of a model setting that in which an agent could sort of illustrate its ability to do these things, you could imagine, let's say, a robot that's sort of dropped into the world. It has no prior knowledge. It doesn't understand anything. And its job is to basically learn everything that it needs to know and perform some tasks. So maybe that robot, maybe its goal in life is to, make as much money as possible for its owner or something, if it's owned by a business. The problem setting that captures the kind of challenges that real biological systems have to solve is basically one where this robot is sort of catapulted into the world and it's now starting from scratch to figure everything out. And that's a really difficult problem setting. It may be that this agent would need to do tons of things before it even gets the first inkling of a success, before it gets the first bit of reinforcement that actually tells it something useful about what it's supposed to be doing, sort of what its purpose in life is. And maybe it's no accident that people spend a lot of time wondering about what their purpose in life is. Maybe this is genuinely a difficult problem. So one of the ways that this problem can be illustrated that I actually like quite a lot is this so-called Yann LeCun's cake. So those of you that have seen some talks by Yann LeCun will have seen this slide, but for those of you that haven't, I can walk you through it really quickly. The idea behind the Yann LeCun's cake is that reinforcement is a very impoverished signal. So if what you're doing is you're learning from seeing essentially a scalar value that says, like, are you doing well or you're doing poorly, just in an information theoretic sense, you're getting very little information from every single observation you make. Right, so in a discriminative learning system, a system that maps inputs to outputs, the amount that it learns depends on the number of bits in the input and the number of bits in the output. And if the number of bits in the output is 0, meaning the outputs are always a constant, the learning system doesn't actually learn anything. It'll just learn to output that constant. So it's not just about how complex the observations are, it's also about how complex the outputs are in the supervision. And the more bits you have in the output, the more information you're essentially getting from each training sample. So the point of the cake is that the reinforcement learning is this kind of, in his analogy, is this little cherry on the cake because it's just giving you one little scalar value for each of your observations. Traditional supervised learning, kind of like the image classification type stuff, is the icing on the cake, and these are his words, not mine, because they're giving you 10 to some relatively small number of bits per sample, more than one scalar, but not too much. But the bulk of this thing is actually if you can do some sort of unsupervised or predictive learning. Because if you're doing unsupervised or predictive learning, what you're doing is you're transforming all of those bits in your input into output. So standard, let's say, generative modeling is trying to model the input distribution, which might be extremely high dimensional. Those are your high bandwidth sensors. Predictive modeling, where you're predicting the next observation, that's also dealing with the entire set of high bandwidth sensors. So that's where you can get a lot of bits of output. So, of course, the argument from this is that, well, if we'd like to get this robot that's catapulted into the world and asked to do complex reasoning to actually behave intelligently, we'd like to make use of all of the bits of supervision that we can obtain from unsupervised or predictive learning. And this is actually, in some ways, was, I think, part of the message in Parsa's talk earlier as well, with the auxiliary objectives. Okay, so this is kind of one view of the world, that maybe this says that if you want to do kind of the more general, intelligent agents thing, perhaps you need to think beyond maximizing rewards and into really incorporating objectives that give you more bits of supervision. Now, that's, of course, one of a number of answers. So the question that this is an answer to is, where does the supervision come from? And Yann LeCun's cake is one of those answers, which is that it comes from unsupervised or self-supervised learning, or perhaps model learning, so learning to predict the future. And this is a very different view on model learning than the standard model-based RL. So standard model-based RL says that, well, if I learn a model, it'll be easier for me to get a policy. And this is more like saying, if I learn a model, it'll get me the right representation. And then generative modeling of the world. Now, Yann LeCun's cake is not the only piece of the puzzle. You could, there are a number of other hypotheses, and I'll just sort of list maybe the three of the most popular ones. So another hypothesis that, well, maybe it's not about setting up the right kind of predictive or unsupervised learning algorithm. Maybe it's about imitation and understanding other agents. So the argument here is that, well, if you catapult a human into the world who has no memory of anything and doesn't know how to do anything, maybe they won't fare so well either. People don't exist in a vacuum. We learn from other people. We have culture and so on. A person who hasn't learned anything from other humans would be, no more capable than a caveman at doing more complex tasks. So we're social animals for a reason, and there's a reason actually that generally the more intelligent animals are, the more likely they are to be social animals. So perhaps the answer really is not to try to build the perfect learning algorithm over here, but to try actually to figure out how to appropriately acquire skills from other agents by watching them. So this is sort of a view of the world that says that imitation is actually one of the primary ingredients, not just sort of a secondary thing that helps you along. And maybe this is worth thinking about as well. And then the third hypothesis is sort of the giant value backup. So this is saying that, well, yeah, it's one scalar value, but you're not actually learning to predict reward, you're learning to predict value. And value is a really complicated signal because value involves the reward backed up over the complex dynamics of the system. So even though it's one scalar value, it's actually a really complex scalar value. And that really complex scalar value is going to actually contain a lot of information about the future. So this basically says that forget all this stuff, just develop the right reinforcement learning algorithm, and by virtue of the value function being, in fact, a rich reward signal because it implicates all the dynamics, maybe you'll actually still do all right. So this is sort of the RL purist view. I don't know which one of these is the correct answer or if it's some combination of these, so maybe it's all of the above. But it's sort of worth thinking about kind of which view of the world makes more sense to you and which view is one that maybe if you're considering future research in this field is something you'd like to pursue. And then just the last point I wanted to make is, well, if we are interested in trying to tackle some of these questions, if we want to understand, is it the giant value backup or is it the cake or is it something else, how should we go about this? I think one of the things that's really important to keep in mind in this field is to pick the right problems. So it's, especially in machine learning, there's often a very strong temptation to go after the benchmark tasks, which serve very well to kind of allow different research projects to build on one another and compare. But think back to that robot that's sort of catapulted into the real world without any prior knowledge. That's a very different problem setting than something like learning to play Pong, where you have actually a very specific, very well-defined goal, and you know exactly when you start succeeding what it is that's going right. So in fact, picking the right problems is something that a lot of the top research groups in this area think a lot about. And for example, a very popular benchmark suite like OpenAI Gym, that's something that I think a lot of you kind of know and love. But in fact, even at OpenAI, they're looking very actively at more complex tasks. So of course, the natural evolution to Gym, I would have expected to see OpenAI Galaxy first, but I guess they went straight to OpenAI Universe. So OpenAI Universe, I guess, is the universe of all things that you can do in front of a computer screen, which is a richer set. And of course, you can imagine that if you go into things that are actually in the real world, maybe they're not quite sort of catapulted to the middle of the jungle and asked to survive, but at least some reasonable proxy. There you might also get a rich set of problems that you can look to try to really understand what are the key challenges in these areas. So it's important to pick the right problems, think through sort of what are the ingredients of an environment or the ingredients of a task that would really kind of exercise the agent's ability to act intelligently. There's this old idea in AI that if you try to solve a problem that doesn't actually require intelligence, it's impossible to actually develop an AI algorithm. So make sure that you pick a problem that actually requires intelligence. And then, make sure to pay attention to things like generative models, prediction, and other concepts that are perhaps somewhat outside of the RL mainstream, but might be implicated in things like representation learning and so on. And imitation learning would also fall under this category. So I think it's important when thinking through these things, make sure that you're aware, based on what you're working on, what is the sort of the supervision hypothesis that you're implicitly subscribing to? Is it the big value backup or the imitation or something in between? Okay. Well, that's it for today's material. I think, is there somebody in the room right now for the course evals? I think they were supposed to, okay. So do you guys have any questions? Okay, excellent. So we'll resume with the rest of the project presentations next week, and those will just be all project presentations, so there won't be any more stuff from me. And yeah, for the rest of today's lecture, we'll have course evaluations, and I'll step out of the room for that. Thank you very much.